talk is about weakening certain information in the sense slightly different from the one presented by Stephen. So the context of this work concerns weighted propositional logics. So weighted propositional logics are very simple but important tools to represent a certain information in compact way. So what is a weighted knowledge base is simply a set of pairs. The first item is a propositional formula, like in classical propositional logic. And the second item is an uncertainty degree, often between 0 and 1. And the intuition behind this pair is that the formula, the propositional formula phi, is certain to, or at least certain to, or at most certain to, it depends on the interpretations, to a degree L phi. So it's not fully certain, there is some uncertainty. So the uncertainty can be a probability measure, it can be a necessity or possibility measure, it can be a mass function, and so on. It depends on the used uncertainty framework. Now, given this set of uncertain information, in general, how it works for defining inference or answering queries. So it works in 2 steps. The first step is from this weighted base, we will define a set of uncertainty measures, either probability or possibility or a mass function, that satisfies the weighted base, that satisfies the constraints given by the user. So this is the first step, it's selection of a family of feasible uncertainty distributions. Then to answer queries, either we use the whole uncertainty distribution for the whole probability or possibility distribution, or we use some general principle, like for instance, maximum entropy in probability, or specificity principle, like in possibility theory, to select one or a subset representative uncertainty distributions, and then we ask queries over this subset. So clearly, the behavior of the inference relations depends. When I say behavior, it depends with rational properties or, for instance, computational complexity, depends on the used uncertainty framework. Whether you use one uncertainty or the other, you will get different properties. One may be rational, satisfies rational properties, the other no, and so on. So in this talk, we are interested in a non-probabilistic framework called possibility theory. I will just give very brief introductions. Basically, the main concept is a possibility distribution. It's just a function that assigns to each word a value, a degree, between 0 and 1. And this value, pi omega, what it represents, to what extent this interpretation, this word, this solution is compatible, is consistent with user preferences, user constraints, and so on. So we just evaluate. User give you preferences, constraints, information. Then for each solution, we evaluate to what extent it's compatible, consistent, coherent with it. And we have some normalization conditions. It simply means there is at least one solution that satisfies all users' preferences. At least one solution that satisfies all constraints. One solution which is fully compatible, fully coherent with available information. Here is a very simple academic example. This represents my beliefs, what was my beliefs last week regarding the topic of the invited, the keynote speakers of today, of Stevens. So assume that we have just 3 variables. The first one, the topic will deal with uncertainty, U. The second variable, it will deal with the AGI. And the third, whether the talk will be introductory or advanced. So this possibility distribution expresses my beliefs. It simply states that the most plausible situations are those where the talk will be on both uncertainty and AGI. This is the most plausible, with a preference to advanced talks rather than introductory talks. This represents the two first elements. Then the second, less plausible, are one of them should be in the topic of the keynote speaker. And the most surprising for me is the one where the talk is neither about uncertainty nor about the AGI, and it's an advanced talk. So it's neither about, moreover, it's advanced. So this is the most surprising situation where when I put one, means the most normal, the most typical situations. Okay, just few words, why possibilistic logic with respect to other uncertainty frameworks? What are the benefits and advantages of possibilistic logics? First, it extends propositional logic. What does it mean? If you have only fully uncertain information and there is no uncertainty, so you will get exactly the same power like propositional logic. So this is not proper to possibilistic logic. Many other uncertainty frameworks satisfy this property, but it's a nice property that one would like to have. And the second important point, it concerns inconsistent information. It handles very well, or at least it has different strategies to deal with inconsistency. This is crucial. So if we take, for instance, belief functions, what we will see, or at least most of the work, to the best of my knowledge, of course, did this at the semantic level. For instance, you like work Philip Smith, Jaeger, there are Zadeh, and so on. There are a lot of work. The only thing, for instance, in Philip Smith's work, what is called TBM, the only thing they said, okay, there is a conflict, an empty set. The amount of conflict, the mass associated, the amount of conflict, we'll put it on the empty set. So there is no syntactic handling, so it's really done at the semantic level. For instance, in Bayesian network, it always assume that local probability distribution associated to variables in Bayesian network are assumed to be normalized. Always, it's assumed normalized. There is no room for inconsistency. In fact, in Bayesian network, they assume that knowledge is stable and inconsistency is more a matter of modeling problem which is solved before. Now, another nice property is it has low computational complexity. When I say low, in the sense comparing with propositional logic, the extension to deal with uncertainty just gives a very small extra computational cost, so very small extra computational cost. But it also satisfies rational properties. For instance, it satisfies all what is known as system P of Course-Lehmann-Magidor or rational monotony. Then possibilistic logic satisfies all these properties. However, it's well known that in probability theory, in general, rational non-monotonic logic properties are not satisfied, unless some very particular cases, like infinitesimal probabilities, big step probabilities, or something like this. But in general, they are not satisfied. And there is also another important properties, is that the set of feasible and the set of possible solutions, given some set-weighted information, is never empty. So this is very important. For instance, in probability theory, if one provides this knowledge, even if the conjunction of this information is consistent, however, there is no hope to find the probability distribution that satisfies probability of A is equal 0.3 and probability A or B is equal to 0.5. Okay, so this talk is also about weakening information by forgetting. So it's one way to weaken information. So weakening information is needed when we deal with inconsistent information. When you have different source that gives some inconsistent information, one way to deal with inconsistency is to try to forget one variable, to try to forget to speak of one variable. So we weaken each source by forgetting one variable, and we repeat until we reach consistency. So weakening is very important. This concept is called forgetting. So forgetting a variable or a set of variables from a consistent formula leads to a new formula. What are the requirements? The first requirement is that this new formula shall not speak about this variable because we like to forget this variable. So this is the first requirement. It's very natural. It should be weak in the sense it should be untied from your initial information. What you get when you forget, when you get a variable, you will get a new weak information. And we like to be the strongest one. Namely, among all the formulas that satisfies the two first items, all of them are weaker than this one, and the result of forgetting. So this is minimality. And adding this minimality, because if you like just a weak, just get empty set. If you get, but you like to get some meaningful. You just like to weak only the variable. So you take the strongest informations that forget only the variable. In fact, if you put these three requirements, there is a unique solution. There's just one solution. And the question is how one can extend it to possibility theory and possibilistic logic. To extend it, we first need to compare information contents, because here we have information is weaker, untied from. So we need to define what is a comparison between two uncertain information. When we can say one uncertain information is weaker than the other. And the second point is how to define forgetting variables. So we will follow exactly the same requirement. I start with the possibility distributions or set of weighted formula, because there is one by one correspondences between semantic and syntax. And I called pforget a variable. You would like to forget a variable from a possibility distribution. First, the result should be independent, so no reference to x, exactly in the same spirit. Then it should be less informative. So in fact, less informative in possibility theory is often used but less specific. We often use less specific to say less informative. And I add a third requirement saying that any distributions that satisfies the two first requirements is less specific than. What is less specific? So possibility prime is less specific than pi, if and only if, for each interpretation, it's more compatible in pi prime than pi. Hence, pi prime contains less information than pi. So I have just three slides before finishing, where I present the three results. The first one is that there is a way to give the syntactic counterpart. It's quite technical, but it's natural to explain. Natural counterpart of specificity relations. We can read it easily. If you have two distributions that are issued from two set weighted bases, then we say that one is less specific because less informative. If and only if each uncertain conclusion that can be obtained from the source can also be obtained from the other source. So we say that one is less informative than the other. The second, which is very important, is that the three requirements of forgetting, in fact, leads to marginalization in possibility distribution. So forgetting in possibility distribution is equal to marginalization. And there is a last technical result. We can do it not only at the semantic level, which is often known as expensive. We can also do it at syntactic level, namely on the formula. The idea is very, very simple, even it's a little bit technical. First, if you like to forget a variable, you make two assumptions. The first one, the variable is true. The second one, the variable is false. And then you combine them. And what we show is that the formula given below is equivalent to the p-forgetting. Okay, now some conclusions. So here we have defined forgetting, possibility distributions. And this definition of forgetting is a simple extension what is done in propositional logic. It is based on the concept of information contents, justified by the notion of the information contents. We have done it both at semantic and syntactic level. Just few words, whether we can do it easily on probability theory. So natural definition is to start with the conclusion that we get, namely forgetting is equal to marginalization. However, if we like to justify it with the three requirements, there is a question how to define information content, less informative in probability theory. In fact, if you like to justify forgetting in probability theory, don't use entropy, which is a very natural way usual way to define information contents, but use the concept of accepted beliefs. What is accepted beliefs? Is simply the set of beliefs that have probability at least higher than half. Then we can show that you can recover marginalization from this. Now, if you like to do it, this is at semantic level. If you like to do it at syntactic level, unfortunately, at least from my first tentative to do it, it's very hard to define it at syntactic level. For instance, if you start with a Bayesian network and you say, I would like to forget a set of variables, what is the result? It's very, very hard to get. I mean, it's very, very exponential to get the result of forgetting variables. While in possibilistic logic, it's quite easy. Thank you.
So again, any just very technical questions for Salem or?
Were you here for the morning workshop?
The second part.
I noticed a similarity in the equivalence of forgetting to assuming that the forgotten variable is both true and false to Professor Wan's special theory of relativity function. I wonder if you noticed that similarity also, if you'd like to comment on any correspondence?
Well, the main point here, we based on axiomatic approach with models, counter models, and so on. So I don't know if whether what we propose here about forgetting can be easily done in his framework. So, but of course, but I agree there is some similarities when you say I assume it's true, I assume it's false, and then combine. I see this similarity, but it depends how we combine. It depends what is uncertainty behind.
Right, it seems to be a slightly different way of combining. I think
Yeah.
if I understood
Yeah,
his
it's
model
matter of
correctly, it delays the decision of,
Absolutely, yes.
whereas yours kind of combines them immediately and then that information's lost.
Absolutely.
Okay, thank you.
Thank you.
Next, Sergey Rodionov.